All right, students, here we go. Help video on 8-15 assessment, page 2. All right, number 9, we're taking a look at a single displacement or replacement reaction between magnesium metal and a solution of aqueous silver nitrate. Well, they're telling us that there's a single displacement reaction happening, which means magnesium, which is a pretty active metal, is going to displace silver from the solution. A metal will displace another metal. That means magnesium is more active than silver. Absolutely. Silver is not a very active metal at all. So here we go. Magnesium metal. There it is. Mg. It's going to start off as a solid. We have an aqueous solution of silver nitrate. There's the aqueous. Silver's Ag. If you remember on our polyatomic ions when we learned those, nitrate is NO3. The nitrate ion is 1 minus. They reminded us here that silver is 1 plus, but we probably would know silver is 1 plus because there's often a Roman numeral 1 above silver's column. On the periodic table, you've got copper, silver, and gold underneath the Roman 1, and that's really telling us that there's 1 in the S, and that's the electron that silver is notorious for losing. So silver's 1 plus, nitrate's 1 minus. We're going to crisscross. We end up with AgNO3. That's aqueous. So we have Ags floating around. Actually, for every 1 Mg, we're going to have 2 Ag pluses floating around in there, but we'll get to that in just a second. Magnesium is going to displace the silver. So now magnesium's floating around in solution with the nitrates. The magnesium and the nitrates aren't actually together. They're floating around separately together in the same solution. That's what aqueous means. Water has them pulled apart. Silver will precipitate out of solution. Why is that? Well, silver starts off as 1 plus over here. When it's aqueous, these are still charged ions. But in the reaction, magnesium is going to force an electron back on the silver. So the silver no longer is charged. It doesn't have a charge. If it doesn't have a charge, the polar water molecule has no charge to grab on and hold it in solution. So it will precipitate out. Now, when we're looking at this, where do I get the formula Mg parentheses NO3 parentheses 2 times? Well, magnesium's an alkali metal. It's a second family, Roman 2. It's 2 plus, crisscross the charge down there. Nitrate ion stays 1 minus, crisscross the charge down there. So we end up with 1 magnesium floating around for every 2 nitrate ions. If I have a 2 there, I'm going to need a 2 in front of here. If I have 2 nitrates, I'm going to need a 2 in front of them on the left side. And that means I now need a 2 in front of the silver. Now that makes sense. Magnesium has 2 electrons to get rid of. Silver's 1 plus, so each silver can only take 1. So we would need 2 silvers to take or to have magnesium force electrons on them. Now they want us to write the net ionic equation. Or actually, we should write the net ionic equation. But before we do, we have to remember that the Ag and the NO3s are pulled apart. They're aqueous. So we have NO3 minuses floating around. We have Ag pluses floating around. So we've got to pull those apart. But the nitrates did nothing here. They stayed 1 minus. They were always with the metal, always with the metal. They stayed 1 minus. They did nothing. So the nitrate ion is minus. And it is the spectator ion because its charge did not change. In a net ionic equation, we're looking for the ones whose charges changed. So in a net ionic, you've got to pull apart the silver and the nitrate. And the silvers are 1 plus. So we have 2 silvers at 1 plus. Magnesium starts off neutral. It has both electrons over here. But during the reaction, the magnesium forces each of the silvers to take 1, and it becomes neutral. So on the right side of the equation, the 2 silvers each took 1 for a total of 2 electrons. Magnesium got rid of its 2 electrons. It's 2 plus. So in the net ionic equation, we're just looking at whose charges changed. Magnesium started off neutral. It forced the silvers to take its electrons, so it ended up 2+ right here, floating around in the solution. The silver started off as 1+. They each took 1 electron from the magnesium, with each of them becoming neutral. That's our net ionic equation. Again, the spectator ions nitrates, they did nothing. Spectators' charges did not change. Here we're looking at some things that we learned throughout our experiments. We learned in the decomposition reaction that if a splint goes out when you insert it in a reaction producing carbon dioxide, the splint will go out. So when we insert a burner splint, or let's go ahead, when you insert a burner splint in hydrogen, hydrogen gas is very flammable. It will combust and begin burning. And we learned in our decomposition reactions that when you insert a burning splint into a reaction producing oxygen, the splint will burn much, much faster. We saw that as well, that oxygen being given off can be shown by the gummy bear or Skittle things, where you throw sugar into the reaction and they combust rapidly when oxygen's a product. So if you insert a burner splint and you hear a barking noise or a popping sound, that means something ignited. Hydrogen's the product. If you insert a burning splint in a reaction and the flint's extinguished, we know carbon dioxide's the product, because carbon dioxide is the product of combustion. You need oxygen for combustion, so if carbon dioxide causes the splint to go out, we know it must be produced in the reaction. If you take a burning splint and blow it out, and you insert it in a reaction producing oxygen, that splint will reignite because oxygen will cause the combusting to begin again, letter C. All right, our final set of questions here. Again, we are supposed to establish an activity series. They drop manganese, a piece of solid manganese, in a solution of aluminum ions. No reaction occurs. What do we know? Aluminum is more active than manganese. If you drop a piece of iron in zinc nitrate and no reaction occurs, what do we know? That the zinc ions are more active than the iron. Zinc atoms are more active than the iron. When you see no reaction occurring, the ion in solution, the metal ion in solution, is more active than the metal you're dropping in there. If you drop a piece of manganese in a solution containing zinc ions and you see a reaction happen, what that means is manganese is replacing zinc because it's more active. Manganese can force the zinc to take its electrons. The zinc would actually end up with manganese's electrons. It would precipitate out of solution. We would learn that manganese is more active than zinc. If we drop a piece of aluminum in a solution containing iron, cations, iron ions, and we see a reaction occur, what do we know? Aluminum must be more active than the iron. So reaction 1, we learn aluminum is more active than manganese. There we go. Aluminum's more active than manganese. In reaction 2, we learned that zinc is more active than iron. There we go. Zinc is more active than iron. The most active are here, least active is here. In reaction 3, we learned manganese is more active than zinc. There we go. Manganese is more active than zinc. In reaction 4, we learned that aluminum is more active than iron. Aluminum is more active than iron. Here's our activity series. Letter E is our answer. Hopefully that helps a little bit on understanding the back of this assessment, 8-15. If you have any further questions or I explained something and you ended up more confused, please email me that question. We can set up a meet and go over it together. Or if you would rather, we could make a whole nother video on just one question and spend as much time as we need discussing it. But let me know which questions you have. I'm happy to help. This is an important assessment for making sure that you understand single displacement, or replacement reactions in the activity series. I thank you for watching.